Greetings. So, just before this class started, we were talking about the difficulties in understanding quantum ideas, and they are difficult. The consolation comes from what Feynman observed, that nobody understands quantum mechanics, but as students we make an attempt to understand as much as we can, read more. The only way to understand it is to study more, to learn more. And you will probably get some ideas from some other sources also, some other lectures and other literature. But I hope that we are on the right track. So what we are going to discuss today is a further application of Feynman's path integral approach. And path integral, we have seen, is an equivalent way of doing quantum mechanics. We saw the beautiful equivalence between the de Broglie Schrodinger approach to explain the interference patterns in a double slit experiment, accounted for by the path integral. The Feynman approach, or if you want, you can call it as the Dirac-Feynman approach, because the original idea came from Dirac. So we are going to discuss in this class another important and interesting application of the path integral, which also gives us a little bit of exposure to some very fascinating aspects of the quantum theory, which is in terms of a phase. Normally we don't pay much attention to phase. Atomic physicists will of course disagree, because we take into account phase all the time, and the angular distributions of photoelectrons, or the time delay, the Wigner time delay and everything, it rests on the phase. But then in many situations where you're dealing with the probability densities and so on, the phase gets cancelled out. E to the I theta cancels e to the minus I theta, and then you don't have anything to worry about. The theta doesn't matter. But then there are some aspects of phase which are extremely important, and these are, I'm referring specifically to what is called as the geometrical phase, or also known as the Berry phase, and we will see it in the context of a particular example, which is a very fascinating example, which is that of the Aharonov-Bohm effect. So we will address these issues in this class. So we consider an adiabatic process, and we know, from your studies in thermodynamics and so on, you've dealt with adiabatic processes. Typically, if you set a pendulum oscillating, okay, and then you carry this box, this red box in which the pendulum is oscillating. Let's say it is some room. It can be this classroom if you wish. And you carry this box very gently, very slowly, and carry it, walk with it. When you started, the pendulum is set oscillating in a certain plane, okay, and if you move the whole room, right, then on a time scale, and that depends on this external time scale as opposed to the internal time scale of the oscillation, which is the periodic time of the oscillator, okay. So depending on the relative difference between these time scales. So if you have the external time scale, which is much larger than the internal time scale, then you will not see any significant difference in the mechanical process, right? However, there is a quantum law which is somewhat similar, and this is inspired by the Gelman theorem of the quantum field theory. And this theorem is pretty old, and it addresses a Hamiltonian which is not fully solvable. So, you can solve a part of it which is at 0 and for which you have got the solution at 0 phi 0 equal to E 0 phi 0. So, that part of the problem is solvable. The residual part is H1 and you insert it through a parameter alpha, and notice that the way you have constructed this alpha is such that as time t goes to minus infinity, that term drops out. So, at infinite time in the past, as if the system was consisted of only the part at 0, which was the friendly part, the part for which you could obtain a solution. And then as time grows, as time t becomes 0, which is now, let us say, okay, the instant at which we are having this discussion can be considered t equal to 0, then e to the alpha t becomes 1 and you get the full Hamiltonian. And the solutions to the problem at this point, we hope, can be obtained from the solutions in the past if the solutions are, if the Hamiltonian evolves gently, adiabatically. Okay. So, some of these things I have discussed in a different lecture in one of my other NPTEL course, which is a course on theory of atomic collisions and spectroscopy in unit 4. The 27th lecture discusses this point. So, I will not repeat those points over here. And the adiabatic theorem states that the solution of the full Hamiltonian develops adiabatically from the solution to the Hamiltonian H0. Okay, which is nice, because ultimately you are interested in getting the solutions for the full Hamiltonian, and if you can develop some mechanism, so it all depends on the time evolution operator and so on. So there are some complex aspects which we have discussed in that other course. So I will not go through that, but for the purpose of the present lecture, let us consider this example from Griffith's quantum mechanics, that you've got a square well potential well, and the solutions, you can normalize them, and you have got let us say the ground state solution, you can get the first excited, second excited and so on. And what happens if you change this potential? Gently but surely. So, change it. So, let us consider a particular change. Let us look for a big change, but effected very gently. Okay? We will look for a change which will double the width of the potential. Now, double the width of the potential is a huge change. It is 100% change, right? But we have done it gently, and if you do it gently enough, then if the particle in the original well was in the ground state, it will continue to remain in the ground state. Okay? On the other hand, if the change is not gentle, you suddenly double the width. Okay? So, here are some time scales involved, and the wave function does not have enough time to respond to the change. So, the wave function tends to remain in the eigenstate of the original potential. Okay? So, what happens is that it tends to remain in the original state of the eigenfunction, and this is no longer an eigenstate of the new square well potential, right? And it will need, the solution can be described, of course, because you can write any function as a superposition of other this thing, but then it will not be in a pure state, it will be in a mixed state and having all the components. So, that is the difference between a sudden change and an adiabatic change. Okay? So, we are now talking about adiabatic changes of the Hamiltonian from H0 to H and the wave functions becoming eigenstates of the full Hamiltonian. Okay. The change can be due to some external parameters, and then the eigenfunction will develop into the eigenstates of the new Hamiltonian with the new parameters, but it will remain in the same state. So, watch the subscript n, which is the nth eigenstate of the Hamiltonian H0, will gently develop into the nth eigenstate of the other new Hamiltonian, which is changed because of certain parameters. Okay. Now, in a certain sense, the experiment with pendulum that we did, it could be a real genuine experiment which we are doing in the classroom, because if you set a pendulum in oscillation at the North Pole, right. So, you have got the pendulum oscillating and the earth under that is rotating, okay, one rotation every day. So, the plane in which the pendulum is oscillating would seem to rotate to an observer on earth, right. So, that is the kind of pendulum that we are considering, okay. And now you move that pendulum adiabatically from the North Pole to a point E1 on the equator. Okay. So, it is oscillating in that plane. Now, you move it on the equator from E1 to E2 and now take it back along the another longitude to the North Pole, all right. And notice that the plane of oscillation is no longer what it was. Okay, do you see that? The plane in which the pendulum is oscillating. So, this is an adiabatic process that you have carried out very gently, but then you end up with a change, but in some sense it is not a change. So it is like a change without a change, okay, right? Because at every instant of time you think that it is oscillating in the same plane as it did. So, it ends up at an angle which is theta. And what is this angle theta? It is a certain fraction of 2 pi. Remember that, okay. And if you look at the angle theta, you want to determine what this angle is, then you can see that the surface area that you would have swept inside this as you travel with the pendulum, okay, complete the loop and come back to the original point. That surface area, you are in the northern hemisphere, right. So, the area of the sphere is 4 pi r square, right. On the northern sphere you have half that area, which is 4 pi r square by 2, and the angle that you are looking at is the fraction theta over 2 pi of this. So, the area swept will be 4 pi r square by 2 multiplied by theta over 2 pi, right. That will be the angle, but it will, if that area is delta s, it would subtend a certain solid angle at the center, which will be delta s over r square. So, notice that theta is equal to omega irrespective of the shape of the contour. Okay, this is a very interesting result, and we are going to get a result which you will be familiar with, but getting it using just geometry. So, this is the angle theta and omega, right, and it has nothing to do with the shape of the area that you have traversed around, right. You have gone round that along its perimeter, but then you have ended up with a change thinking that there would be no change, and you have a system which has not returned to its original state when transported over a closed loop. So, such systems are non-holonomic. Okay? Such systems are non-holonomic. The Foucault pendulum is what we have been talking about. So, this is an example of that. And the Foucault pendulum actually, instead of us physically carrying it over the sphere, it is the sphere which is rotating underneath. So, it has the same effect. Okay. So, now if you look at the Foucault pendulum, which is a non-holonomic system, you look at the solid angle subtended by any perimeter. That solid angle is a integration over theta and phi. What is this? The solid angle subtended by a latitude at the center of the earth. It will be integral over phi and sine theta, integral of sine theta. So, this will be 2 pi coming from integration over phi, the azimuthal angle phi, right, and then you have integral of sine theta d theta from 0 to pi. So, you see that this turns out to be 2 pi into 1 minus cosine theta 0, right. So, what it means is that cosine theta 0 is the same as sine of the latitude, because latitude is measured from the equator and not from the north pole. That is the only difference, but otherwise you have essentially the same angle. And you see that the daily shift, which is 2 pi cosine theta 0, which is equal to 2 pi sine of lambda, it depends on lambda. So, you know by what angle the plane of oscillation of the Foucault pendulum has dropped, and from that you can calculate how long it will take to come back to the original plane, which will be the reciprocal of the frequency, right. So, from the reciprocal of the frequency, you have got this result straight from geometry, not doing any other analysis. Okay. This angle is incidentally called as the Haney's angle in classical mechanics, right. But from the reciprocal of the frequency, you get the periodic time which goes as 1 over sine lambda. Okay. And this is just the result you would get if you take into account the Coriolis force, if you did this analysis in a rotating frame of reference. Okay. And I have worked this out in details in this book, Foundations of Classical Mechanics. This is equation 3.34 in this, where the details have been worked out. But there you do this entire analysis in the rotating frame of reference, carry out the transformations from an inertial frame to a rotating frame, and then arrive at this result. Over here, you get it just from geometry, okay, which is really very, very nice. So, we are now going to work with quantum systems, which are subjected to non-holonomic adiabatic processes, and the changes are brought about because of a Hamiltonian which depends on an external parameter r. Okay? And the question is, how does the final state differ from the initial state? Okay? If the parameters in the Hamiltonian are changed adiabatically, and then you bring back the Hamiltonian, you change the parameters so that after the changes you get the same set of parameters that you had originally, and then does it leave the system with any change or not, like the plane of oscillation ends up changing, right. So, let us consider the Schrodinger equation, and you have got the quantum system in the nth eigenstate. Now, in the previous unit we discussed the time evolution of the Schrodinger states, and the time evolution of a stationary state is essentially given by e to the minus I omega t. Okay, omega is e over h cross. This is the time evolution of a stationary state. I mentioned at that point that this is the dynamic phase, the e to the I theta, where theta is et over h cross, is the phase angle, this is the dynamic phase angle. This is the dynamic evolution of the state of the system. A stationary state evolves with time, it is not static, it does evolve with time, and the evolution is given by this phase angle. And if the Hamiltonian becomes something different at a later time t, but the evolution, the change from h to a later time Hamiltonian is adiabatic, then the system continues to be in the nth eigenstate. Okay? And this is the Schrodinger equation that its eigenstate will fulfill, and the nth eigenstate will depend on time, it evolves with time, and the evolution will involve the dynamic phase. Okay? The dynamic phase is here, but in addition to that, nothing stops you in quantum mechanics to think that there may be another phase which possibly is detectable, which is I gamma e to the I gamma t. So gamma is this additional phase. So you have got the usual dynamical phase that you considered, and now you have another phase which is the geometric phase, which is coming from this parametric variation of the Hamiltonian. So this is the geometric phase which is going to be the subject of our interest in these few classes. Okay? So this is also known as the Berry phase, but this is there intrinsically in quantum mechanics, except that nobody had paid much attention to this till Berry did. So energy is not conserved in this process because the Hamiltonian is changing, and there is some agency involved in changing the Hamiltonian. So that would be pumping energy or extracting it out of the system. So energy is not conserved, and that's not the issue here. All right. What is important is that the system continues to stay in the nth eigenstate. Okay. So at a time t double prime, the energy will be En t double prime, right? So this is the Schrodinger equation, and let us now consider the possibility that there is a little bit of departure from adiabaticity. Okay, we have assumed that it is a strict adiabaticity, but if it is not, there is a slight departure from strict adiabaticity, and that is measured by a tiny parameter. You can call it as a perturbation parameter kind of thing, which is a measure of departure from strict adiabaticity. In that case, the wave function at the time t will be different from the wave function when you started because of the dynamical term, dynamical phase and the geometrical phase, but not only of the nth term. This is what you would have if there was strict adiabaticity, which we had on the previous slide, but now that we are talking about a departure from adiabaticity, which is measured by the tiny parameter epsilon, then you can have an admixture of all states m not equal to n. So the wave function will be given by this, and it is this wave function which you must insert in the Schrodinger equation. So insert it in the original Schrodinger equation. So h operating on this full wave function equal to IH cross time derivative of that full function. Okay. So let us carry out this analysis on the next slide. Okay. So you have to take the time derivative of two terms on the right hand side. One is this, the second is epsilon times this, but this is a product of three terms. Okay. So you do it term by term. First term, derivative of the first term times the remaining two terms, then the first term and the derivative of this dynamical phase term, which will give you minus I over h cross En, right, times this e to the I theta, right, and then the third term, and then you have got the first what is it, the first and the second term, and then the derivative of the last term, which is del gamma by del t times e to the I gamma t. Okay? So, it is nothing serious. The equation looks, it seems big only because it is covering the whole screen, but it is a very tiny equation with very few, pedestrian terms. So, some of these terms are going to cancel. Those which are underscored by red, you can see, are equal on the left hand side and the right hand side. Okay, there is an IH cross outside the bracket, so that cancels the minus I over H cross, and then the two terms on the right and left cancel each other, right? And that makes the equation look a little bit smaller. It's the same equation nonetheless, right? And let us analyze it further. Okay. You can now write it for this term, these two terms which correspond to the nth state. Everything else is the sum over m for m not equal to n, as you have on the left hand side, and also on these terms on the right hand side, this one and also this one, right. So, you just write it for this term, bring it over here, and all the other terms on the opposite side of the equality sign. So, you have got a minus sign here, and then these two also go with a minus sign. So, you get minus I epsilon common, then you have a sum over m not equal to n, and then all of these terms. Got it? Okay. So, that is what we have here. And now you bring this phase factors from left to right. So, they had a plus sign here, and on the right they come with a minus sign here. That is all that has been done. Okay. And remind yourself that the parameter epsilon is a measure of the departure from strict adiabaticity, right. So, on the left hand side you would have terms in the first order in epsilon, because those terms are coming in the first place only because there is a departure from adiabaticity. If there was no departure from adiabaticity, those would go to 0. Okay. On the right hand side also there are some terms which are first order in adiabaticity, right, in departure from adiabaticity, right. So, e to the minus I gamma n is nearly equal to 1. Okay. So are the last two terms inside that rectangular bracket, but then the remaining term is of second order, because it is not only coming from psi m, but a variation in m. So, psi m itself is coming because there is a departure from adiabaticity. Okay. So, you have a second order term and you can neglect it. So, having neglected the second order term, the equation now becomes smaller. Okay. Now, let us analyze this result. So, this is what you are left with, and notice that on the right hand side m equal to n is completely excluded, and although I did not mention earlier, which I perhaps should have, you begin with an original orthonormal basis, so that when you take a projection of both the left hand side and the right hand side on the state psi n, then from the right hand side you get essentially 0, because in the superposition that was left, the m equal to n was already excluded. So, now you have an equation for d gamma by dt, right. Gamma dot is d gamma by dt. So, let us see what we get for that. So, d gamma by dt is this, because the I comes with a minus sign on the opposite side. Okay. Now, the wave function is changing with time, but the reason for this change is that the Hamiltonian is changing because of some other control parameters R. So, the derivative of psi with respect to time primarily is because r changes with time and psi changes with r. So, del psi by del t is del psi by del r times del r by del t. Okay? And this is a derivative of gamma. Gamma is the geometric phase or the Berry phase, and you can get this by integrating this equation. So, you integrate from some initial set of parameter Ri to Rf, and the geometrical phase is given by this expression at the bottom of your screen. The changes are brought about, remember, because the Hamiltonian itself is varied parametrically. So, if you change the parameter, if the final parameter is the same as the original parameter, then you can see that this vanishes and there is no big deal about it. But what happens is that when it changes not just on one parameter, but on multiple parameters. Okay? So, then you get some very interesting physics, because the partial derivative with respect to r is now a set of partial derivatives, and they all go into what will become a gradient in the multi-dimensional R parameter space. Okay? We normally think of the gradients in 3 dimensions, but the same idea can be extended to n dimensions, right? So, you have got a gradient operator in a multi-dimensional parameter space R, and del by del R will have to be replaced by the gradient of R. And in this case, it turns out that the geometric phase in general is not 0. So, this was recognized by Michael Berry in a very celebrated paper in 1984, and this is a very readable paper. I strongly encourage you to read Berry's original paper. It's a wonderful paper to read, and in general this is not 0. And notice that the Berry phase does not depend on the time taken, except that the changes have to be adiabatic. They cannot be too sudden. Okay, so there is a time factor which is involved, but in an indirect way, not in a very direct way. Okay? The dynamic phase, on the other hand, explicitly depends on time. So, the dynamic phase depends on time, the Berry phase depends on the path of integration and not on the time. So, Berry was born on the pi day. You know what is pi day? Everybody knows. So, pi is approximately 3.14. So, March 14th, third month, 14th day of March is called as the pi day, and Berry was born on pi day, and so was Albert Einstein. So, which is why the pi day is so important. And this is a classic paper, Quantal Phase Factors Accompanying Adiabatic Changes, by Michael Berry in 1984, Proceedings of the Royal Society of London. And now we have this adiabatic change in the state psi to psi into a dynamic phase multiplied by the Berry phase or the geometric phase. Now, if you look at e to the I gamma, if gamma was imaginary, e to the I gamma would become e to the minus I minus something, and this would actually represent attenuation or damping rather than a phase. Okay? On the other hand, if gamma is real, then it becomes a phase. So, we should first convince ourselves that we are looking at a phase and not attenuation. You can do it by recognizing that the original functions are normalized. Okay? So, the gradient with respect to r of the norm must vanish, and now if you write it as two terms, you immediately see that the real part of this is 0, and therefore gamma itself would be a real number and therefore a phase factor. It is not attenuation, so we do not have to worry about that possibility. Okay? So, this is a phase as we expected it to be, right? We also know that if the wave function is real, so will be the projection of its gradient or the same state, and then the factor that you have in the integrand is both imaginary and real, and it can therefore be only 0, right. So, which means that the geometric phase would vanish if the eigenphase functions are real. So, this thing is not of much interest when you have real eigenfunctions, but in other situations it is of some interest, and that is what we will discuss in the next class. Okay. So, for the moment I will stop here, and we will continue from this point in the next class.